Okay, thank you. Okay, welcome back. Welcome to part 2. So we'll keep this a bit short. I just want to discuss one quick application of the dependence theory, which probably you have seen before, but I think it's just a very cool application. Right, so I won't tell you a result. I'll just tell you a moral of the story, if that's okay. Sometimes an application is more philosophical. Right, so what is a solitary edge? A solitary edge of a matching code graph is any edge that belongs to exactly one perfect matching. Okay? Any edge that belongs to precisely one perfect matching in a matching code graph, right? And interestingly, we don't understand them that well. We understand a few things about them, but there is a lot we don't understand about them. And one very nice question that comes from Schoenberger's theorem, 1934, right? So Schoenberger proved that every two connected cubic graph is matching covered. So every edge belongs to at least one perfect matching. So it is natural to ask, what are those edges that belong to exactly one perfect matching? Right? And this is something that has been researched recently, as you know. Right? So there have been a couple of papers where discuss solitude, the state of being solitary, in two connected cubic graphs. Right? But you can ask more generally for matching code graphs. Can you give a complete characterization of solitary edges? Of course, from a polytime point of view and all that, it's not very interesting. Delete the two ends of the edge and check whether the remaining graph has a unique perfect matching. This can be done in polytime, not too difficult. So in that sense, it is not very interesting. But from a characterization point of view, it is interesting. Can I just look at a graph like this one and tell you immediately where all the solitary edges are? Right? In that sense. So here is the question. So what happened is, this is the problem we decided to start working on when Narayana started his thesis, right? And before Narayana, there were a couple of others who had worked. One of them was Kalyani. She was an intern for some time, and she had also worked on this problem, solitary edges in two connected cubic graphs. And interestingly, the first, or one of the early offerings of this course, which is nothing compared to this offering in terms of how much I'm covering and all that. But one of the offerings was in 2022-2023, December, January, before you joined the program, right? And Aditya and Narayana were the only two people enrolled in that course, right? That was a contact course, not this regular course. And I was teaching the dependence relation, and Narayana decided to take that concept and throw it at his problem, solitary edges. And what happened afterwards was really fascinating, right? So here is the most important observation from Narayana's thesis. If you have a matching code graph G, an edge E depends on an edge F, and F is solitary. Then what can you say? E depends on F, F is solitary. Then what can you say? Because most of you have already seen this, so I can just probably ask anybody. E depends on F and F is solitary. Then what conclusions can you draw from here? F depends on E and E is also solitary. Then observe that F depends on E and E is also solitary. Yeah? Is that correct? this has some interesting consequences. If you have an equivalence class in a matching covered graph that contains a solitary edge, then what can you say about that equivalence class? What can you say about the other edges in that equivalence class? All of them are solitary. If one edge in an equivalence class is solitary, then so is every other edge in that equivalence class. What else can you say about a solitary class? So we can now use the word solitary class. I can say that an equivalence class is solitary if some member, therefore every member, is solitary. What else can we say about such equivalence classes? Where can they be in the dependence poset? Minimal, right? Solitary classes are minimal, right? So equivalence classes may be partitioned into solitary and non-solitary classes, where solitary means each edge is solitary and non-solitary means no edge is solitary. And second is that every solitary class is a minimal class. Yeah? Let's look at this example. In this example, the bicon, one can check that every minimal class is a solitary class. This one, and this one. In general, this is not true. In this example, each of them is a solitary class. In general, this is not true. Of course, no discussion in the world is complete without the Petersen graph. So we might as well discuss the Petersen graph since we haven't discussed it so far. In the Petersen graph, every edge belongs to precisely two perfect matchings. And no edge depends on another edge. That is also true for the Petersen graph. In the Petersen graph, the dependence digraph or the dependence poset is very useless. It's very uninteresting. Every element is just a single edge and there are no dependencies. This is the empty poset. And the relationship set is empty. So in particular, every edge is a minimal class, a removable class, a removable edge, but no edges are solitary. So in general, minimal classes need not be solitary. One extreme example is the Petersen graph, where there are no solitary edges to begin with, right? But what is the whole moral of the story here? The moral of this story is that don't study solitary edges. Study solitary classes. That is what should be studied. Right? And that is what I mean by application. The application is study solitary classes. Not edges. Right? And this essentially, I would say in some sense, apart from all the theorems and all that, I would say this was sort of the main contribution of Narayana's thesis. Study this, not that. Right? Yeah. So in fact, to complete the story, there was a paper in 2024, I think, or 2023, I forget the exact year, by 5 authors. Gertgeber, Mattiolo, Mazzucolo, Renders, and Wolf, that studied solitude in 2 connected cubic graphs, and they proved some results. One of the results they proved is that there are at most 6 solitary edges in a 3 connected cubic graph. And Narayana proved a stronger version. Narayana proved that not only are there at most 6 solitary edges, there is actually some nice pattern to them. In particular, Narayana proved that there are at most 3 solitary classes, and each solitary class, because it is a removable class in this context, its cardinality will be 1 or 2, which is one of the results we'll prove. We'll prove that every removable class in a matching chord graph has cardinality 1 or 2. So that is one result that Narayana used, the main result of this chapter, along with at most 3 solitary classes. 2 multiplied by 3 gives you 6. So you have at most 6 solitary edges as a corollary. Right? So with that, I will conclude discussion of this application, and I will just state that the next main goal but this is not yet, we are not yet there, we still need some more things, but I'll just state it anyways in the language we have discussed so far. Corollary 8.18. In a matching covered graph, every minimal class, not minimal, removable class has cardinality 1 or 2. Okay, this is what we will conclude this chapter with. Right? Okay, any questions, concerns so far? Okay, but before we get there, let us continue studying dependence. Any issues?
You know some graph where solitary or
Removable, yeah. So it is not true for minimal classes. Minimal classes can be larger. One example is just even cycles. Right? In an even cycle, each perfect matching is a minimal class, and clearly its cardinality could be very large depending on the cardinality, the size of the cycle. Right? But they are not removable, because you delete that perfect matching, now your graph is disconnected. So this removable really requires this connected is the main point. This is what distinguishes minimal classes from removable classes, just special types of classes. Okay, so what we'll do next is we will try to understand dependence a bit more. E depends on F. Let's try to understand this better. And E and F are distinct edges of a matching chord graph G. Yeah? Fine. So let's try to see what this means structurally. E depends on F, so that means if I delete F, then E is no longer in any perfect matching. This implies that in G minus F, E is unmatchable. But the graph G minus F itself is matchable, right? Do we all agree? G minus F is matchable. You delete an edge from a matching chord graph, which is not K2 because there are two distinct edges. The remaining graph has a perfect matching. However, G minus F is matchable. What does this mean? Why is E unmatchable in G minus F? What can we say? Go back to the beginning of this course, right? Don't forget all of that. Right? So why is the edge E unmatchable in G minus F? What makes an edge unmatchable? Okay, let me know if you raise a hand. Yeah. Raise a hand if you know, or if you have figured out something.
I got confused.
Okay, so why is the edge unmatchable? What makes it unmatchable? Think about the times before we knew what tight cuts were. No tight cut, nothing. Just I'm looking for something in terms of barriers. Right? So, because the graph is matchable and E is unmatchable, we know that in G minus F, there is a barrier that contains both ends of E. Right? So let's draw this. G minus F. There is a barrier. That contains both ends of E. So E looks like this. Yeah? Notice that we can't say anything about the even components of G minus F. There may be even components. It's not a matching covered graph. Right? If it were a matching covered graph, we could say that there are no even, but it's not a matching covered graph. In particular, you have a barrier that is unstable. Right? There could also be even components. I've just not drawn them conveniently. Right? I've just hidden them. They could be there. But what can we now say about the edge F? Now I want you to think about, where is F? Or rather, where are the ends of F, because F is not there. Where are the ends of F in this drawing? Where are the ends of F? Remember, G is matching covered. So in G there should not be any barrier that is unstable. So when you introduce the edge F, you must kill this barrier, right? Because you can't kill its lack of stability, right? So you have to kill this barrier, and therefore the only way to kill this barrier by including the edge F is if F has its ends in distinct odd components of G minus F minus B, right? So if I want to go back to the graph G, then this is what F looks like, right? Okay, we have proved a couple of things actually. I'll just write them down. An edge E of a matching covered graph G depends on another edge F this is how we started. If this is the case, then we concluded that G minus F has a barrier that contains both ends of E. Yeah? Observe that if this is true, if G minus F has a barrier So think of deleting f. If G minus f is a barrier that contains both ends of E, then it actually means that B is not matchable in G minus f. E is not matchable in G minus f. That means E depends on f, because E was matchable in G. So if it is not matchable in G minus f, that is because every perfect matching containing E contained f. So therefore, the other direction is easily clear. Right, so that's what we proved. So that is QED. And another statement we proved, well, I'm stating it like this because I'm pretty sure Lucchesi Murthy are going to use it later. Another statement we proved here is the following, that if for a matching covered graph, after you delete the edge f, there is a barrier containing both ends of E, then it means that the ends of f are in distinct dot components of G minus f minus B. Right? So G is a matching covered graph, and f is some edge. If G minus f has a barrier that contains both ends of some edge E, or I could have just said that is not stable. Then f has its ends, maybe I should say the ends of f is not there actually. Then the ends of f lie in distinct odd components of G minus f minus B. This is the other statement we proved. Yeah? Okay? So that is what dependence looks like structurally in a matching code graph, right? This picture basically captures dependence. E depends on F. This is what it looks like. Now we'll go one step further, and we will also finish mutual dependence. Let's try to see if we can figure out. Clearly for mutual dependence you will get this drawing. Can you say more? That's where we are going. Okay, this is the last part for today. We have a matching chord graph G. We have two distinct edges, E and F. And we have the fact that E and F are mutually dependent. Okay? So then what all can we say? We can definitely reach this point. Let me actually draw this again. Okay, I'll draw it here. This is G minus F. Let me now actually put even components. And the edge E is here, I'll draw it like this now. And if we introduce the edge f back into the picture, then we have something like this. But now we have mutual dependence, right? This figure we got by assuming E depends on F. But we also know that F depends on E. So can we make more conclusions with regards to this figure? Of course, you can make a separate drawing for replacing F and E, but that's not what we are going to do. We are going to stick to this drawing, right, and make more inferences over here. This barrier is not stable. In particular, it contains both ends of E. Can it contain both ends of another edge? Could there be another edge, E prime? Is this possible?
different outcome, because now any edge within the barrier depends on F. So E prime depends on F. We assumed F depends on E. So E prime also depends on E. So ends of E should be distinct outcome.
No. Ends of E will be distinct out components of G minus E minus B. First barrier.
Minus B, yes.
Thank you. I'll give you a hint. Your best friend is perfect matchings. Okay, don't make other friends. And I'll give you one more hint. SGT assignment 5 was for a reason. There were specific problems in SGT assignment 5 which have a thought process that is useful here. Right? There was a problem where you had a barrier, and you had to explain the structure of any perfect matching with respect to a barrier. You had to explain that if you restrict the perfect matching to an odd component, you will get a near perfect matching of the odd component. If you restrict it to an even component, you will get a perfect matching of the even component. Right? Of course, here you are using the generalized definition of barrier for all graphs, but well, it also works for matchable graphs, matching cover graphs. Right? So think about all that. What did you do there? Supposing there is an edge E prime like this, like the one I have drawn. E and E prime could be adjacent, don't worry about that. I have drawn it non-adjacent just for simplicity. But E prime is in a perfect matching, no? E prime is in some perfect matching because graph is matching covered. Now think. Complete your perfect matching. E prime is in some perfect matching. Take a perfect matching M containing E prime. Now complete the drawing. See what happens. How will you complete it? So, yeah, so the point is, if there is an edge like this, E prime, take a perfect matching containing this edge. I won't even make drawings here. Take a perfect matching containing this edge. Okay? I have 3 vertices here remaining. I have 5 odd components. That's a problem. Unless I use this edge. So I better use F. I have to use F. That perfect matching has to use F. Now I have 3 odd components and 3 vertices. 3 equals 3. I must match each of these odd components into one of the remaining vertices. That means E is not used. So I have a perfect matching containing F but not containing E. Contradiction, because E and F are mutually dependent. Therefore, we just concluded that there are no such edges. Right? So, E is the only edge with both ends in B. Okay, let's see if we can make more conclusions. This is what the barrier looks like, right? This is an honest drawing of the barrier. Only one edge inside it. The rest of it is actually stable. It is quasi-stable, if I may call it. Right? Good. What else? Can there actually be even components? In fact, what I would like you to think about now, I would like you to think about perfect matchings of this graph. There are 2 types of perfect matchings. Those that contain E and F, and then those that contain neither E nor F because of mutual dependence. Right? Either a perfect matching contains both of them or it contains neither of them. Those are the only 2 types of perfect matchings in this graph. Right? I want you to think about both types of perfect matchings and see if you can make some more conclusions. Right? One is regarding the even components, and can you make some additional conclusions regarding the odd components? In other words, consider a perfect matching M such that E and F both belong to N, and consider a perfect matching N such that neither E nor F belongs to N. Answer. And based on your drawings, see if you can arrive at some additional conclusions.
is negative or intersects that cut. So it has to be the entire vertex set.
What has to be the interpretation?
This part.
Okay, then there are no even components. There's one more conclusion you can make about the odd components. So now think about okay. So let's consider a perfect matching, blue perfect matching, which contains both E and F. Right? So let's just draw it. I have to use the edge E, I have to use the edge F, but I have to match all the vertices. I have these three odd components, and I have three vertices here. Right? So the only way to finish it is, without loss of generality, do something like this. And now you complete the perfect matching here, complete the perfect matching here, complete the perfect matching here, here and here. That I can do. I mean, if there is a perfect matching containing E and F, it has to look like this. And observe that it doesn't use any edges between even component and the barrier. Right? Blue perfect matchings cannot use any edges. So yeah, I think the way Santosh explained it was nice. So look at this cut, separating the even components from the rest of the graph. The blue perfect matching meets the cut in zero edges. Now let's consider the pink perfect matching. Pink perfect matching contains neither E nor F. It contains neither E nor F. That means you can just ignore E and F. I have 5 odd components and 5 vertices. I have no choice in life. Without loss of generality, I have to do something like this. Then complete it here, complete it here, complete it here, blah blah blah. Again, observe that we are not using any edges from this cut. Therefore, edges from this cut will not belong to any perfect matching. The graph is matching covered. Therefore, there are no edges in this cut. That just means that this set is empty. Right? That means there are no even components. Right? So we concluded that there are no even components. G minus F has minus the barrier, has no even components. Yep. Yeah. But there is something else we can say based on these two perfect matchings. These two perfect matchings are representative in a sense. They are representative of all perfect matchings in this graph. So what else can you say about these perfect matchings with respect to these odd components? Do you see something nice? There is something nice going on. For each odd component, consider the corresponding cut. Right? If you see an odd number of vertices, you should think about the corresponding cut. Odd cuts are very important in matching theory. So what can you say about the perfect matching's intersection with the cut? 1. Right? Each perfect matching meets each of these odd cuts in precisely one edge. Therefore, these odd components are shores of tight cuts. Right? So the one more conclusion is each odd component, or let me just say partial of K, is a tight cut for each odd component. Oh, I don't need to say odd anymore. K of G minus F minus B. Yeah. All right. We got a bunch of tight cuts. Of course, they could be trivial tight cuts. Right? We are not saying they are non-trivial tight cuts, but they are tight cuts for sure. In fact, now I am so tempted that I want to say something which is coming up in chapter 9. Supposing G is a brick, if G were a brick, what can you say about all these odd components? Then they are all trivial. If G were a brick, then all these odd components would be trivial. That means that G minus E minus F is? G minus E minus F is? Bipartite. This is a thing Loas proved much before many other things were proved. One of the things Loas proved, if in a brick you have two mutually dependent edges, E and F, then G minus E minus F is bipartite. It need not be matching covered actually. That is a false statement. G minus E minus F need not be matching covered, even if G is a brick. If it is matching covered, then what you have is a near bipartite brick. But in general, that is not true. In general, you can have two edges in a brick that are mutually dependent, which means that G minus E minus F will be bipartite. But it need not be matching covered. You can make examples yourself. Yeah. But yeah, anyway, so that is something that comes up I think in chapter 9. But yeah, I was just too tempted to not state it. Right. So anyway, so this is basically 8 point something. What is it? 8 point. Oh, it's here. 1.3. Yeah. What I just wrote down is basically 8.13. 8.12 is missing here. 8.12 is a very technical statement that I will not write down today. I will just state it next time and we will discuss it. But I'm guessing that they will. So what they do is they prove this very technical counting lemma. Its statement is like really obnoxious, and then they just use it to prove everything in 8.13 using that counting lemma. We basically did not go through that. We bypassed 8.12 and we directly observed all of these things, right? But I'm guessing that they will use this later, so I will just state it anyways for the sake of completeness. Yeah. So what we have today is we have seen the dependence relation. We talked about a bunch of concepts, the dependence poset and all these things. And then we also looked at some structural relations, results about dependence and mutual dependence. If you have dependence in a matching code graph, then you basically have this drawing that we had earlier, right? But at that point we couldn't say if there are more edges, if there are even components. Then we assumed that we have mutual dependence and we were able to make more conclusions that are all written over here, right? So yeah, so that's all for today, and we continue on Monday. Our next main goal is this corollary I stated, which I think I raised at some point, right? We want to eventually prove that every removable class has cardinality 1 or 2 in any matching code graph, right? And one more quick announcement is on Thursday next week, we will have a guest lecture by Rishikesh Gajala, who did PhD with Sunil Chandran. He said he would like to visit and come over. I said, okay, you want to give a talk? So he works on problems, which are basically problems on matching code graphs, coming from quantum physics and all, which I don't really understand. But yeah, so we will have a guest lecture by him on Thursday, and we will have our 2 regular lectures on Monday and Wednesday. Yeah? Okay, that's all for today. Are there any questions or concerns? Okay, thank you, and see you on Monday. Have a nice weekend.